This section, we look at the inverse of the exponential function. We look at the logarithmic function and how to take the derivative of that. We're going to first just take the derivative of the natural log of x, and then we're going to see when we have more than just x, how we could apply what would be called the chain rule to the natural log of x. And then the last thing, we're going to use those properties of logarithms and use logarithmic differentiation to find dy dx. So let's start out with, how do you take the derivative of the natural log of x? First of all, if you notice, we have these absolute value signs. And so we are restricted to taking the natural log of things that are greater than or equal to 0. Actually, just greater than 0. Because the derivative of the natural log of x is just 1 over x. So x cannot be 0, but here x needs to be greater than 0. When you have something more than just x and you have a function of x, the derivative is the derivative of what you're taking the natural log of, that goes on top, divided by the function itself. Or just like in the last video, I like to use the u substitution and say the natural log of u is du over u. Now this isn't great English, but this is all I've got, is that it's the derivative of what you are taking the natural log of, that's on top, divided by what you are taking the natural log of, du over u. So let's just practice a few of them. Again, these are the odd ones from your book. Right? So the derivative is, that's going to always be the denominator. And then you take the derivative of that, which is 1. I'm going to work number 5 two different ways, and then let's discuss the easiest way. Right? Taking the derivative says put that on the bottom, and then take the derivative of x to the 8th. And now let's simplify that, so that would reduce to 8 over x. So that's one way. Another way to do number 5 is to use those properties of logarithms and rewrite the original function. Remember, we can take that exponent and move it down in front, and then take the derivative. So I would leave the 8, and the derivative of just the natural log of x is 1 over x, and we get the same answer. Sometimes using those properties will shorten our work by quite a bit. So on problem number 7, that's the square root of x. I want to rewrite that as x to the half power. Now I could take the derivative by putting that on the bottom and then taking the derivative of that on the top, but I'm going to use those properties, and I'm going to bring that half down in front. Now that's just the function. I have not taken the derivative. Now here comes the derivative. Leaving that 1/2, all I have to do is take the derivative of the natural log of x, and that's 1 over x. And I think that is going to be much easier by using those properties. So let's look at number 9. Okay, remember, 1 over x squared is the same as x to the negative 2. Bringing that law, I can bring that down in front. And now taking the derivative, once again, I'm just taking the derivative of the natural log of x, which is 1 over x. That's why we did those properties. If you need to go back and review, that's in section 2 of chapter 5. Now this one looks scarier, but keep in mind we cannot distribute across a parenthesis. So the derivative is going to be, all of that is in the denominator, and then the derivative of that goes in the numerator. That's it. So looks scary, but really quite easy. right? Well, number 13, this is where you're going to see where those properties really pay off. So I have some students that would work this the hard way, and they'd go, oh, well, let's just put this in the denominator, and then we'll take the derivative of that using the quotient rule. Oh, that's just terrible. But let's just use those properties of logarithms to say if I have a log of two things divided, I can rewrite that as the log of the top part minus the log of the bottom part. Then I can take the derivative of each of those separately so much easier. So the 2x goes in the bottom, the derivative of 2x is 2, the x plus 1 goes on the bottom, and the derivative of that is 1. And the only thing I'm going to do is reduce out those 2's, and that's my derivative. So much easier than going through all that quotient rule. You might want to find a common denominator, but this answer is fine by me. Right, so as I look at number 15, I do see a product. I can't use any properties of logarithms because it's the product of something that's a log and something that's not a log. So let's just use that product rule. So the derivative of x squared is 2x. The derivative of natural log of x is 1 over x. I'm going to cross multiply and add. So I have, let's see, 1 over x times x squared plus 2x times the natural log of x, and then just reducing, I think that's just going to leave me an x. There you go. Now the reason why I like to do these side by side is to see the difference. Okay, this is number 19. You have the natural log of u minus 2 cubed. Okay. On this one, it is the natural log of x all raised to the 1/2 power. That is not the same as the natural log of x to the 1/2 power. Okay, this one you cannot use the rule where you bring that down in front because that does not apply to the rule. All right, this one you could, okay, but that's not the same. So on this problem, we can use that rule that allows us to bring that exponent down in front of the logarithm and then take the derivative. So the u minus 2 goes in the bottom, the derivative of that is 1, and you're done. But what about number 21? We have f of x equals the natural log of x to the 1/2 power. Taking the derivative, we're really going to use the power rule, chain rule. The chain rule, the power rule, let's just review that. If I have x to the 1/2 power, that's 1/2 x to the negative 1/2. So this is going to be 1/2 times the natural log of x to the negative 1/2. So that's part of the power rule. But then we have to take the derivative of the inside part, which is 1 over x. So be very careful about those exponents, where they are, and so if the whole thing is in parentheses, you cannot use this law of logarithm that we used up here on number 19. I'm just going to go ahead and rewrite that as all in the denominator. And I'm going to put back that square root sign. Be very, very careful. Okay. So 23 and 25 is another example of that. So number 23, this whole thing is in parentheses, so I cannot use my properties of logarithms, but I can take the derivative. You bring down the 3, subtract 1 from the exponent, that's that power rule, and then take the derivative of the inside. Row number 25, can I use any properties of logarithms? No, I cannot. I cannot distribute. This power is not over the whole thing, so I just have to take the derivative. So the derivative would be this in the denominator, and the derivative of that is 3x squared. That goes in the numerator, and you're done. All right, so now we're going to mix up some e's. So here we have definitely a product rule. We have e to the 2t. Those are my two functions. Taking the derivative of e, remember it is the original function times the derivative of the power. Here, there's a denominator. The derivative of that is 1. So I'm going to multiply and add. So number 29, my derivative is e to the 2t times 1 over t plus 1 plus 2e to the 2t, natural log of t plus 1. And you can leave your answer like that. You don't have to find a common denominator for me. Right on 31, of course, you're going to need the quotient rule. So let's see, that's the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. So I'm going to reduce that. That leaves you x, all divided by x to the 4th. And I think we could go ahead and reduce that since they all have an x. Let's divide out one of those x's. So that's going to be 1 minus 2 times the natural log of x over x to the 3rd power. Right? We're asked to find the second derivative. So we're going to find the first derivative first. Can't simplify that. Now, notice we don't have a natural log. So we're going to have to use the quotient rule. So the bottom times the derivative of the top minus the top times the derivative of the bottom, all divided by the bottom squared. So I think this is a very interesting problem because we go from the natural log to not the natural log. Let's see, if I distribute that, I think that's all you can do with that problem. Now let's look at logarithmic differentiation. That sounds really scary, but it's not so bad. Our answers are going to look atrocious, but the process is pretty easy. We're going to take the derivative, and they're going to be such terrible functions that you would not want to take the derivative by using the chain rule or quotient rule or anything. It would just take you forever. But we can use those properties of logarithms to help us out. So what we're going to do is, first of all, we're going to take the natural log of both sides. Right? And now we're going to use those properties of logarithms to rewrite this right-hand side. So as you remember, we have these products, so we can write this as addition. And we're going to keep using those properties of logs by bringing those exponents down. Oops, that's a 2. Okay. Now, much less complicated. The second step says to take the derivative of both sides of the equation with respect to x. So the derivative of the natural log of y is 1 over y times dy dx. And that's what we're looking for. Now, The right-hand side is all just x, so that's going to be, when I take the derivative, it's just going to have that dx over dx. You may remember that from a couple of chapters ago. And then, of course, that's just 1. So I'm not going to write that part. All right, so taking the derivative of this, going to have 2, the denominator with the numerator, then the 3, and the 4. So what we've got is 2 on top of this fraction, 3, and 4. And this all equals to 1 over y times dy dx. All right, so how do we solve the resulting equation for dy dx? Well, if I want this by itself, then I just need to multiply both sides times y. So we could say dy dx equals to all of this times y. But what was y? This is where your answer is going to be really ugly. So we're going to have dy dx equals times y. Y was the original problem. And you can leave your answer just like that. You could do a lot more simplification, but let's not. Okay, so the process once again is to take the natural log of both sides. So I'm just going to be lazy and so I'm taking the natural log of that. And that's going to allow me to use those laws of logarithms. And remember that square root is the half power. Now keep going with those properties of logarithms till you get rid of all those exponents. Okay, so that's my natural log of y equals that. That's the first step. The second step says to take the derivative. Right? So I'm going to have 20x, multiplying that together. Then those both go in the denominator. All right, that's a minus sign between there. So that's dy dx, and I'm going to do a couple of steps in one. Now I won't. So that's 1 over y times that equals that difference. Now I want to solve for dy dx. So I multiply both sides by y. All of that times y, but y was the original function, so multiplying times y, and that's dy dx using logarithmic differentiation. Let's do one more. Ooh, we have an x in the exponent. That's quite different. So step 1, take the natural log of both sides. Then use your laws of logarithms to get rid of any exponents or products or quotients. So I'm going to bring that x down in front. Then take the derivative of both sides with respect to x. So now I have a product. All right, so here are my two functions I'm taking the product of. Okay, so I'm going to multiply and add. So it's going to be I'm just going to write that a little bit nicer. Okay, so that's dy dx times 1 over y. And then to get this by itself, we want to multiply all of this times y. And y is your original function. And there's dy dx. Not that hard, just kind of scary looking. Don't be afraid, just go for it.